We will be discussing about image interpretation by the visual method. And later when you progress in the module lectures, you will also be discussing how the same kind of information extraction can be done using digital image analysis. So by now you are well versed and familiar with this process of remote sensing, wherein we need an energy source. Energy from the source travels, in this case, the energy source is the sun, and energy travels, that is electromagnetic radiations, travel through the atmosphere. While traveling through the atmosphere, there is interaction between the constituents of the atmosphere and the radiation. Then it reaches the feature of interest, that is the surface of the earth, and interacts with all the features that are there, but whatever it encounters, the radiation encounters, that is built up areas, vegetation, water, barren areas, and so on. After interaction with the features on the surface of the earth, energy or the radiation is reflected or backscattered towards the sensor and gets measured in the form of a digital number, and these digital numbers are integrated to form an image, which is then supplied to users for further analysis. Before we begin interpretation, you must have already discussed it, but I'm stressing on the fact that as users of remotely sensed data or image data products, we must be familiar with the electromagnetic spectrum and its properties, and how these properties are manifested after the interaction of the electromagnetic radiation with the targets that we are dealing with or the features that we are trying to interpret. So basically, as we say, the electromagnetic spectrum ranges from shorter wavelengths, which include X-rays and gamma rays, to longer wavelengths, including microwaves, that is radar wavelengths, and communication wavelengths used for communication, that is radio waves. Now, there are several regions of the electromagnetic spectrum which are useful for remote sensing. Now, once we have these interactions recorded in the form of an image, then with this data set, we can go for image interpretation. So we will be able to say that the analysis of remotely sensed data or images will involve the identification of various targets or features in the image. Now, these targets or features can be identified in terms of the way that they will reflect or emit or backscatter radiation. How much amount of radiation, in which wavelength band, under what physical condition does the target reflect or emit, will be measured in the form of a digital number on the image, and this is to be analyzed by the interpreter. Now, as we know that the radiation is measured and recorded by a sensor, and this is what is ultimately depicted as an image data product. So therefore, we can say that the act of examining these images or looking at these images critically to identify objects and also to judge their significance, that is to see them in relation to each other and what significance do they have in the context in which they occur. So we can also say that this interpretation or visual extraction is also, visual image interpretation is also an information extraction process from the images. And it will involve a considerable amount of subjective judgment on the part of the interpreter. An interpreter would be a specialist who is trained in the study of photographs or images. And in addition to this, he or she should also be an expert in some discipline, that is some scientific discipline or some subject. Like a geologist could use these photographs for geological studies, that is for identifying areas where there are specific minerals, or to study landslide prone areas and so on. There could be several such geological studies. A biologist or a forester or an agriculturist could use these images for their particular areas of expertise. Now, let us quickly go through and revise characteristics of images. Image, as we know, is a pictorial representation of an object or a scene. It could be analog, that is hard copy, or it could be digital, a digital image. The structure of a digital image is such that it is made up of square or rectangular areas, which we term pixels or picture elements. As you can see in this figure here, it is an array-like structure which has rows and columns, and this translates into individual cells or pixels, as we call them, picture elements. Now, each pixel has an associated pixel value, which depends on the amount of reflected energy from the ground. So whatever features occur in this area covered by one pixel will reflect some amount of energy in that particular wavelength band. Now, since our sensors are capable of operating in multiple regions of the electromagnetic spectrum, we can have multispectral images. In fact, these days we also have hyperspectral images. So there are numerous hundreds of very narrow contiguous bands which let us distinguish between even similarly reflecting objects. Now the question arises as to why do we need to be specially trained in the study of interpreting objects from airborne images or satellite images, wherein in everyday life we are used to looking at images and identifying objects that we see on these photographs or images. Basically, what we are doing is in everyday general interpretation, we have access to three-dimensional view through our eyes. However, when we look at single mono images, we lose our sense of depth, and when we view this two-dimensional image, unless we are able to see it stereoscopically, this is a special technique wherein we need at least two images taken in a specific manner so that we are able to simulate the third dimension of height. So there are several cases of confusion when we look at objects in a two-dimensional image, which is a single image. Then viewing objects from directly above also provides us with a very different perspective than what we are familiar to viewing in everyday life. Usually, when we are viewing terrestrially, we do that with a horizontal viewing perspective. But when we take images with a camera mounted on an aerial platform or on a space-borne platform, the viewing direction becomes vertical. So we are only able to see the scene or the objects from a vertical perspective, and then we are only able to see or visualize them, the top of those objects. So we need to train ourselves to be able to adjust to that unfamiliar perspective of viewing and then analyze what these objects could be when viewed from a vertical viewing perspective, or when we are able to see only the top of these objects in the scene. Then combining the unfamiliar perspective, viewing perspective, with variable scales and lack of recognizable details can also make the most familiar objects unrecognizable in the image. So there might be confusion based on this aspect also, because the sensors will have different pixel sizes and therefore it will translate into different spatial resolutions. So the same object that we see on the ground in a particular size could appear smaller or larger depending upon its spatial resolution. Then we as human beings are used to seeing only through the visible wavelengths, that is from 0.4 micrometers to about 0.7 micrometers, the VIBGYOR section of the electromagnetic spectrum. And the imaging wavelengths outside of this window we are not able to decipher those or see through those. So it is difficult for us to analyze how objects would look like through these unfamiliar wavelength, in these unfamiliar wavelength regions. Therefore, we need to train ourselves again, like in the case of the vertical viewing perspective. We need to be familiar with the behavior of these wavelengths in respect to the features or the physical condition of the features that we are trying to assess or comprehend. Then we come to very important aspects of the characteristics of the data or the specifications of the data in terms of spectral resolution, radiometric resolution, spatial resolution, and the temporal resolution or the revisit time. So these four characteristics basically will, or the four kinds of resolutions will basically dictate or tell the user what would be the optimum kind of data that he or she should use for the particular kind of application that he plans to implement. So spectral resolution is assessing which part of the electromagnetic spectrum is being measured and what is the bandwidth. How narrow are the bands in which the image is being captured or the data is being captured. So this will help us to distinguish between similarly reflecting objects. Then radiometric resolution translates into subtle changes in energy. Can those differences be, is the sensor sensitive to these differences, small changes, minor differences in energy? Can it measure those as distinct entities or not? Spatial resolution, as has already been discussed, it is the amount of detail or the smallest unit area that the sensor sees at one instance of time. This is the simplified way of putting it. So this translates into the amount of detail that we can see. So the finer spatial resolution, that is at say 1 meter, we will be able to see objects in more detail, greater detail, as compared to say a spatial resolution of 10 meters where the details will become limited. Then temporal resolution, as the name itself is suggesting, would be the time gap between two successive image acquisitions over the same area. This characteristic comes in very useful when we are trying to study we do change detection or see what changes have happened in a particular area over a period of time. So how much forest has degraded? Has there been deforestation? Have urban areas encroached into forest areas, or has agriculture area increased, or has agriculture area encroached into forest areas, and so on and so forth. Also, in case of disasters, in the occurrence of a disaster, pre-event images and post-event images can be used to assess the amount of damage and spatial locations of where that damage has happened, and then it can ultimately be used for planning the recovery operations and so on. Now, what is the advantage of using images over ground observations? Because ground observations would be more accurate. We would have pure data for signatures, for classification, etc. through ground observations. However, this kind of technique provides us with a synoptic view. So we are able to see a large area, and we are also able to see objects in relation with each other. So how does does it affect the other object in its vicinity, or does it not? What could be the effect of these surroundings that has on the object itself? Images are a permanent record, so we can keep revisiting these. So in terms of change detection, this could be helpful. It also lets us see in different spectral regions. So some characteristic property which possibly the visible region of the spectrum does not let us interpret could be better interpreted, say, in the infrared wavelength region, or maybe the thermal wavelength region, or possibly the microwave region, and therefore it would give us the ability to better make better distinctions between different object classes. Varying spatial resolutions also let us see things in different scales, and at times this is a very useful property. Since we are able to see a large amount of area, and this reduces our manual work, so the technique turns out to be cost and time effective. So it's more economical in terms of both the money aspect and the time aspect. Sometimes it is very critical. Suppose if there is a disaster and we don't have time to visually analyze, say, hundreds of images, these kind of, we don't have time to go, and the area may also not be accessible. So image data or remote sensing data comes in very useful at such times. Stereoscopic data or stereoscopic views or processing techniques also give us additional information in terms of heights of objects. So we can generate digital elevation models and use this data for further planning activities. We've already discussed that context can be seen. So we can see objects in relation to each other. So interpretation becomes easy. Now we come to the next section as to how the actual interpretation is done, based on what characteristic. So whenever we start identifying objects, suppose we start identifying human beings or people we know, identity is established by some signature or some entity which is a characteristic feature, and this forms the key to enable that object to be identified. Now, these signatures can be based on spatial, spectral, temporal, and polarization variations, which will facilitate the discrimination of features on remotely sensed data. So it is something like when you go to the bank, you are asked to put your signature, and that signature is compared to the archived or sample signature that you have already provided. Now, if there is a match, then you are able to carry out your transaction. Similarly here, when signatures using ground observations are compared with the signatures that we are able to extract from the data, that image data that we have, we are able to compare them and then come to a conclusion about which objects could be which features on the image, or which pixel values correspond to which features on the ground. Now, this is done through spectral reflectance curves, which is a graph of the spectral reflectance of objects plotted as a function of the wavelength. So in this graph, if you see, on one axis you have the wavelength regions, and on the other axis we have the amount of reflectance in percentage. So if we look at individual features, let us take the first feature, water, which is clear water. Now the physical condition of the object here becomes very important, because the spectral signature and the spectral signature reflectance curve will change as soon as the physical condition of the object changes. So if it is clear water with no pollution or no suspended material, then the spectral signature is such that very little, say about some 5% of the energy is reflected in the visible portion. And as soon as it reaches the near infrared region, all the energy is absorbed. All the water feature, all is absorbed by the infrared region, in the infrared region. So if we look at the image, the water features will appear dark in the infrared band, and in the visible portions there will be very little amount of reflectance. Now, whereas if we compare this with vegetation, now the physical condition here says green, so it has to be healthy green vegetation. So here if we see, in contrast to water, the infrared region gives us high amount of reflectance. So this green vegetation will give us a bright feature, will be seen as a bright feature in the on the image. Also here we see there are some absorption dips at specific locations. So these are also specific. This will also tell us about the water content in the plant cell. So whether there is less amount of water or the plant is water stressed, these things will be indicated through the spectral reflectance curve. Similarly, dry, bare soil also gives us high reflectance throughout. So dry, bare soil will be bright feature. So if there is a barren land which is very dry, it will be seen as a bright feature. However, if we add water, or there has been maybe some irrigation or some water content, moisture has been added, then it will give us a darker manifestation on the image. So the spectral signatures are very significant in terms of the spectral responses that are measured by the remote sensors over various features. Then spectral reflectance and spectral emittance curves can be generated. And the variability of spectral signatures is useful for the evaluation of the condition of the physical condition of the object. Temporal and spatial effects on spectral response patterns can also be studied, and we can look at changes that have happened over a period of time. Now, with this, we can look at spectral signatures for common land cover classes like vegetation. So this is the curve for vegetation, spectral reflectance curve for vegetation. So here, if you see, the general characteristic of vegetation is its green color, which is caused by the presence of the pigment chlorophyll. And since chlorophyll reflects green energy more than red and blue energy, this is what gives the plants its green color. Now, due to any reason, the amount of chlorophyll decreases in the plant cell, then this shape of the curve will also change. So if it is a diseased vegetation, or due to some natural reason, that is growth, change in growth stage, etc., if the plant becomes any other color than green, the curve will change. Or if the plant naturally does not contain chlorophyll. So the presence of chlorophyll is what is of importance here for high reflectance in the infrared region. Then other major physical features that the reflectance depends upon is the thickness of the leaf. So if it is desert vegetation, that is if it is a cactus kind of plant or succulent which has thicker leaves, and if it is other kind of plants which have thinner leaves, then the amount of reflectance will be different, because the amount of absorption and reflectance from these physical features, because of these different physical features, will also be different. The type of leaf or the structure of the leaf, that is if it is a needle-like leaf as in coniferous forests, which has less surface area for reflectance, or if it is broad-leaved or deciduous leaves, the kind of reflectance will change. The stage of growth, young plants, there will be reflectance from the surroundings also, because they will be small plants. So the soil might also, the surrounding soil will also contribute to the reflectance. Whereas when it is mature, it will be purely from the plant, and after certain stage of maturity, it may change its color from yellow to, while harvesting, some plants may change into yellow or gold color. So those aspects, physical changes, will also be reflected in the spectral reflectance pattern or curve. Now, health of the vegetation will also affect the amount of reflectance. So if there is some disease due to which leaves have become yellow or brown, or they have curled up, so these diseased plants will be, as compared to the healthy plants, the amount of reflectance will be different, and this will be reflected in the, or manifested in the spectral reflectance pattern. Now with this, we can just spend time to analyze what we have just discussed and revisit the basic section through this question. You can attempt it later. What is image interpretation? There are three options, and you can, after looking at the slides or going through the material that is provided to you, you can assess the correct answer. Then the next land cover feature is the spectral signature for soil. Now, soil is also affected by the characteristics of how much moisture it contains, whether it is dry soil or wet soil. So wet soil will generally appear darker, and increasing soil moisture content will lower the reflectance. Then how much amount of organic content it has, how much manure, etc. we have added to the soil. Structure of the soil, that is it porous or is it compact structure like clay and sand. So this will dictate how much water absorption capacity it has. So in sand, more absorption will happen because the soil particles are loosely packed. Clay is compact and therefore it will hold more water. The amount of iron oxide content and the texture of the soil. The texture and structure are connected to each other. So organic content, again, less decomposed organic material will have higher reflectance in the near infrared region, and more decomposed will give you low reflectance throughout the reflective region. Iron content again, so reflectance in the green region will decrease with increased iron content, but this increases in the red wavelength region. Right? So iron dominated soils will have a strong absorption in the middle infrared region, that is more than 1.3 micrometers. So here strong absorption will be there. So in case of absorption, it will appear darker. So structure and texture. So clay soils tend to have stronger texture or more compact texture, which leads to rough surface on plowing. So clay soils will tend to have higher moisture content. As a result, they will have fairly low diffuse kind of reflectance. And sandy soils, on the other hand, will have low moisture content. So a high or specular reflectance properties will be shown. Then if we consider water, so spectral signatures of water are affected by of course, the wavelength region in which we are looking at the feature, that is water. The depth of water, whether it is shallow, near the land water boundary. So suspended material will also have, will contribute to this, the reflectance. So deeper water bodies will have, in the infrared region, it will give us darker manifestation, it will appear as a dark feature, whereas shallow water bodies or regions where the water is shallow, that is near the coast, some amount of reflectance may be contributed by the suspended material, or because of the shallowness, the coastal shelf may also contribute. Suspended material will give some amount of reflectance. Chlorophyll content like algae, etc., if it is there present on the surface. And surface roughness. Is it a calm standing water body, or is there much turbulence due to wind, etc., or movement of ships, boats, and so on? This surface roughness is also a very important characteristic when we are looking at these features in the microwave data, and there this roughness becomes very important and a very critical characteristic for interpretation. So visible wavelengths of the EMR, as we have seen in the curve also, and it is depicted here as well. Visible wavelengths, there is very little light absorbed. So small amount, usually below 5%, is reflected and the rest of it is transmitted. Water absorbs strongly in the near infrared and middle infrared region, and therefore this results in a dark manifestation on the image, and a sharp contrast between what land water boundaries can be observed. Now, if we talk about snow, then this is affected by, say, grain size and therefore the age. So reflectance falls at or becomes low at wavelengths as the grain size increases. The thickness of the snowpack, so reflectance of the snow decreases as it ages. Amount of liquid water content. So if there is even slightly melting snow, which has some amount of water content, this reduces reflectance. Now, if you analyze, the snow feature gives us high amount of reflectance. So features which are snow features or glaciers appear as extremely white, bright features on the image. However, because water reduces the reflectance, that is, it contributes more to absorption. There is more absorption because of water in the infrared region. So melting snow will be affected by this water content, and there will be reduced reflectance. If there are some contaminants or pollutants present, these also tend to reduce snow reflection in the visible region. So with this curve, you can analyze which features to observe and how distinctive the curves are for each feature. So for clear water and turbid water, for wet soil and dry soil, and for snow and clouds. Now they are both very bright features on the image because they reflect highly, but there are certain ranges of the electromagnetic spectrum that we can use, and we can look at the spectral reflectance curve to help us make a separation criteria for these two similarly reflecting features or objects which appear similar on the image. Similarly, vegetation, but different kinds of vegetation, say coniferous vegetation and deciduous vegetation. So once we start visual image interpretation, we can do an analysis of which bands give us the best possible information about making a distinction between the features that are present. So if we display individual bands of a multispectral image, we expect to see them as black and white grayscale representations. And here, if you see the amount of contrast in these images, if you see here with the infrared band, so water and the other features become more distinguishable because of good contrast between these, whereas the boundaries here are not so well visible. So we can choose optimum bands or best bands for the interpretation activity. Similarly, multispectral images can be displayed as either a true color composite or a false color composite. So a true color composite, as you know, will depict the features in the natural, in the way that the feature naturally occurs on the terrain. So water features will appear in shades of blue depending upon their depth. So if here it appears that there is a shallow area, and as we go in, it becomes deeper in the reservoir. Also near the land water boundary, again, we can observe some shallowness. Dry river areas appear to be very bright features, and green is all vegetation, different shades of green. Now the same area is depicted as a false color composite, that is to accommodate the limitation of the display system, because the display system has only 3 color guns and we may have more than 3 bands to display. So we need to choose the 3 best bands for display purposes. Please note, it is only for displaying, the limitation is only for physical display. However, algorithms and other aspects, digital aspects, can be run on all the number of bands, as many bands as we have. So this is a standard false color composite. And here we see vegetation in shades of red, sand and built up areas in cyan tone. So you will see that cyan occurs in the sandy, dry sand area, riverbed, and also wherever there is built up area. Vegetation is seen in different shades of red. Similarly here, so the band combination is again IR, R and G. So here again we see dry riverbed with water channels and a reservoir here, one more reservoir here. Shadow areas also appear to be similar, giving us similar reflectance to water. Bare mountain area, bare slopes, forested areas on the slopes, then dry riverbed, agriculture area with both cropped fields and fallow areas. And here you can also see with the pattern that there is an orchard. This, however, because it is vegetation, so the reflectance is similar. Now, methods for image interpretation, as we said earlier also, that they could be visual. So we could adopt a totally visual manual approach, that is, interpret it on a hard copy photograph or image and manually interpret it. Or we can use a hybrid approach wherein we display a digital image on screen and do the interpretation visually and manually digitize those features, groups of pixels. The second method could be totally digital, that is, we need digital images and we process those images using some algorithms or programs. So here for this discussion, we are going to focus only on visual image interpretation and how we are going to do that. So the interpretation can be qualitative and quantitative. So we can make qualitative assessments of whether the feature reflects more, it reflects less, absorbs more, and so on. So it is a bright feature, a dark feature, a gray feature. The shape of the object is such, the texture is so and so, and so on. Alternatively, we can also have quantitative measurements like areas, lengths, heights, depths, and so on. So what we should remember is, however, that similar objects, because we are looking at reflectance values, so similar objects under similar conditions will reflect similarly. So like the examples that we saw in the previous images. Sorry. In the previous images, so there we saw that the shadows and water gave us similar reflectance, although they are different physical features. Also, urban areas and sand, dry sand, river sand, etc. also gave us the same kind of reflectance. So the factors that we need to consider for good interpretation are, of course, training and experience of the interpreter, what kind of features or phenomena we are trying to study, quality of photographs and equipments, and whether we have adopted the correct method of interpretation, whether we have proper kind of interpretational aids, and are we familiar with the area that we are trying to interpret. So these are all that will help us do better, improved interpretation. Then we can summarize the activities of visual image interpretation under the following categories, that is detection, recognition, detection, deduction, recognition, classification, convergence of evidence, putting everything together, putting all the clues together, and then analysis and idealization. Now, the data selection criteria will depend upon the applications. What is the application that we wish to use this data? Is it for a civil engineering kind of application, or an application where we need to design urban utilities like mapping of roads or laying of new roads or railway lines, etc.? Or is it a study that we need to do at a very high resolution with more detail? Is it something to do with mapping similarly reflecting features like two species of trees? So there we need to look for data which will distinguish between these two kind of data sets, these two kind of features, because they are both vegetation. So we will have to look at higher spectral resolution data and so on. If it is change detection that we need to do, then we will have to look for at least two time data, the pre-event data and a post-event data. So temporal variations will be preferable. Then which sensors and platforms are available, at what resolutions or at what specifications do they provide data? Will it be necessary to use airborne data, or should I use spaceborne data, or should I use terrestrial data, or do I need to integrate the data together, and so on? Then, is the time of acquisition important? Do I need daytime images, or do I need nighttime images, or do I need both images? So for studies like studying fire incidents, say forest fires or coal fires and so on, So this kind of criteria may be important. So here is another question for you to reflect upon. A spectral reflectance curve is what? Is it a graph of number of pixels? Is it a pie chart which represent land use classes, or is it a graph of spectral values of the objects with reference to wavelengths? Please look at it once we have finished. Now we come to the elements that help us in interpretation. So as we have seen that the recognition of targets is the key to interpreting and information extraction. So observing the difference between the targets and their background involves comparing different targets based on any or all of the visual elements. So tone, shape, size, pattern, texture, shadow, and association. These are these elements of interpretation. If we have stereoscopic data, we can also consider height as an element which will help us in interpretation. Now let us quickly go through each of these elements. So the primary element for interpretation, or the fundamental element for which enables us to distinguish between different targets or features, is tone. So tone refers to the relative brightness or color of objects in the image. Generally, tone is the fundamental element, as I said, and variations in tone also allow the elements of other elements like shape, texture, pattern, etc. to be distinguishable. So as you can see here, wherever there is a distinct change in tone, along that we can form an edge or boundary. So this boundary indicates the change from one feature to another. So if we are able to mark out all these boundaries, theoretically we will be able to mark out all the features that are present on the image. Now shape is another element of interpretation, and this refers to the general form, structure, or outline of individual objects. Shape can be very distinctive clue for interpretation because we associate certain shapes with certain features, like linear shapes with roads and railway lines, etc. Square rectangular shapes with agriculture fields, and so on. So the size of the object is the third element which we will be discussing. So this is a function of scale or resolution. So it is important to assess the size based on the spatial resolution of the image data that we are looking at. So size is important because, say, if it is built up area, their buildings may be of different sizes. So if it is industrial area, we may have large buildings like factories, etc. And in residential areas, we may have smaller, different kinds of buildings. Pattern, the element of pattern refers to the spatial arrangement of visually or visibly distinguishable objects. So are the objects repeated in an orderly fashion or not? So if there is a repetition, this generally happens in man-made features. Naturally occurring entities usually do not follow a pattern or a fixed pattern or a fixed arrangement on an orderly repetition. So if we need to distinguish between trees in the forest and orchards, so pattern is an element which will be of great importance. So orchards will have evenly spaced trees, whereas the trees in the forest areas will grow haphazardly. Also, urban streets where there is a planned housing colony will have regularly spaced houses with well-planned streets and so on. So this will also, from the vertical perspective, will give us a good example of pattern. Now, the element of texture refers to the arrangement and frequency of tonal variation in different areas of the image. So this, in simpler words, it means how soon or how frequently does tone change in an area on the image. So if you look at this lower half of the image, it appears to be homogeneously bright, and this gives us a visual texture of it appearing smooth. So visually it appears as a smooth texture, whereas the upper half of the image, there are frequent changes in tone. So very bright, dark, gray, and so on, and shades in between. So we can clearly mark out the boundary based on the difference of texture. So the upper half, because there are frequent changes in tone and tones are varying, so visually it appears to be a rough texture, whereas here it is homogeneous and there is not much variation, so it appears to be visually smooth. Now, texture is a very, very important element for distinguishing features, especially in radar imagery as well, and high spatial resolution optical images also. Then we come to shadow. So shadows are usually taken as occlusions or noise in the image. However, in certain cases, they may provide us or give us an idea of the profile and relative heights of the objects, and which will help us to make the identification easier. So a rough estimate of the height of the objects can also be made, like if it is a flyover, then the length of the shadow, etc., or if it is a building, the length of the shadow can be used for identifying, roughly making an estimate of the height of the building. Now, the characteristic or element of association takes into account the relationship. So it takes into account the context and the relationship between other recognizable features or objects in the nearby vicinity of the feature of interest. Usually, we associate certain features with certain other features. So these associations help us to make accurate interpretation. For example, commercial properties or commercial setups would be associated with the proximity or nearness to major transportation routes. Whereas your residential areas would be associated with schools, playgrounds, and sports fields, etc. So different kind of features will be associated with certain other features. We have already looked at color and true color and false color images. There is another good comparison. So green is vegetation here, and other features indicate the built up areas, roads, buildings, and so on. Here also, if you see, this appears to be a water body, and here these are grass lawns, some trees, and again some vegetation, which is also grass, bushes, etc. Built up areas with buildings and roads. Now, after this discussion, I think you can answer this question very easily. It is related to the element of texture. So with the options given, whether it is a spatial arrangement of distinguishable objects, which we can see visually on the image, or is it arrangement and frequency of the variations of tones in some areas of the image, or is it the structure or outline of the individual objects? Now, I will quickly, in 5 or 10 minutes that are left, we will quickly go through some examples of images so that you get an idea of how varying the data is, and depending upon spatial, spectral, temporal, and radiometric resolution, what are the differences that you can observe and what features you will be able to see in different objects. So this is a Landsat image which has a water body. So infrared band, the water body appears dark. Red is all vegetation. Cyan tones are arid areas, dry sand, etc. This also gives us a very dry, arid region. Small patches of red indicating vegetation. The stream or river, some part of the channel has water, other parts of the channel have become dry. Here it says mid-infrared, so the thermal region must have been included. And this is a volcanic feature, so you are able to see the crater in bright orange or red, and vegetation also appears in red. At the base of the mountain, we have some kind of cyan tone, so this could indicate some settlements. These circular features are sprinkler irrigation systems, and these are particular to dry, arid, desert type of climates. So here there is a lot of sand. The different circular features are agriculture fields, with different stages of crops. Some are lying fallow, some are half cultivated, and the other half of the field is fallow with different amounts of moisture. Some are dry, fallow and dry, some are fallow but with moisture, and so on. So this, some are totally fallow, and this area which is bright cyan tone is sand. Similarly, here we can see in the second image, we can see suspended material and the beach area where there is sand, vegetation, etc. Inland water bodies. This is a delta. So the spatial resolution is also varying. It is IRS 1C, WIFS data, coarse data, medium resolution data, large amount of silt deposited because it is delta region. Here, mountainous rocky terrain with very sparse vegetation. Urban areas again. So here you see this very specific feature, linear feature. This is the airstrip. Other urban features like roads, buildings, etc. This could be a park. Okay. Here it appears to be a stadium and several buildings and roads. Again, another urban setting, but this has more agriculture fields wherein you can observe cropped fields and fallow fields, a water body which has a very fixed geometric shape, so it could be a man-made water body. This feature in particular is a runway of the airport, and buildings and roads with a water body running here through the image. Here you see the rough surface of the water with ripples, and the beach sand is very well visible. A lot of vegetation in red, in different shades of red. Now here the second image, the spatial resolution is sub-meter, that is 70 centimeter. So here we are able to see objects in very high amount of detail. We can mark out the boundaries of individual buildings, chemical tanks, chimneys. We can even see the smoke coming out of the chimney and the shadow of the smoke. So that's an industrial area. Now to highlight the importance of temporal variation in images, if you see here, this is September 7th and this is September 12th. So time difference between the acquisition, and if you notice, this area here is damaged. The building has become damaged, whereas here the building area was intact. So we can do this change detection if we have temporal variation in the data acquisition. You can also observe other urban features like parking lots, shape of buildings, roads, flyovers, etc. in this image screenshot. Here again, you can observe and appreciate the different textures of plowed fields, fields with grass, fields lying fallow and not plowed. Also the orchards here with different species of trees, or maybe different stages of growth of the trees, etc. And these linear features that you see here, some shadows are observable, triangular shadows. These are windmills. These two images are of desert areas where we see sand dunes. So these are longitudinal dunes and these are crescent shaped dunes. Here we have a ridge area. Now these three features are reflecting similarly. They are all bright features reflecting, giving high amount of reflectance. This due to the setting is snow area, snow-bound area, glaciers, because the terrain is very mountainous. These are clouds. The puffy cotton wool type of texture indicates that they are clouds, and also the shadow. This is near the sea coast in the western part of India, Run of Kutch. So these are salt pans where salt is harvested. All these three features, although physically different features, are giving us the same kind of reflectance. So with this, you can appreciate how you will use different elements of interpretation to distinguish between similarly reflecting objects. Now, these are again some urban features. So this is a brick kiln. We are able to see the chimney and the shadow of the chimney, nearby excavations and stacks of brick kilns. Railway lines, a railway station maybe, a flyover, urban areas, built up areas, and stadium can be seen here. Very densely built up area, densely populated area, no pattern visible. However, here it has a visible pattern and high-rise buildings with long shadows. Very, very high spatial resolution, could be an aerial photograph or a UAV acquired image. So you can see even the vehicles on the roads can be counted. The markings on the roads can be easily distinguished. Road dividers, etc. are seen. And on top of the buildings, we can see air conditioning units or water storage units, etc. can also be seen. This is also, again, the second one is an industrial setup. So you can see shed-like buildings for storage, chemical tanks, and so on. Now, this is a exercise for you. After you go through the lecture material, you should easily be able to identify the features marked 1 to 5 and also discuss or analyze which elements of interpretation were helpful in identifying these features. So you can do this as an exercise and test how much you have learned through this discussion. Now, before we wind up, we will quickly do a comparison between manual and digital interpretation. Since you have not yet been exposed to digital image analysis, you will probably be able to appreciate this much better when you have gone through the discussions on digital image analysis. However, manual interpretation and analysis dates back to the early beginnings of the remote sensing, when we used aerial photographs for interpretation mainly. Digital image analysis and processing is more recent with the advent of digital systems and digital systems for recording and computing. Manual interpretation requires little specialized equipment, but digital analysis requires specialized and often expensive equipment in terms of hardware and software. Manual information extraction is also often limited to analyzing only fixed channels or single channels of data from the image at one time. However, the computer environment or the digital environment is more amenable to handling complex images of several or many channels from several sources at one time. Manual interpretation is also a subjective process, meaning that the results may vary slightly with different interpreters. Digital analysis, however, is based on the manipulation of digital numbers with the use of a computer system and is therefore more objective. And this usually results in more consistent results. It is more objective, therefore. However, determining the validity and accuracy of the results from digital processing can be difficult. We saw examples in the previous slides that similarly reflecting objects could give us similar signatures on the image. So the digital classifier could get confused between a shadow and a water body, or it could get confused between built-up areas and river sand, dry sand, which a human interpreter is less likely to do. So, therefore, the ability to do visual image analysis and then use it for validating and using it to calculate the accuracy of the results that we obtain from digital processing is what is to be done. So that is why visual interpretation is very, very important. And we would highlight the point here again that visual and digital analysis are not mutually exclusive processes. In most cases, a mix of both methods is usually employed when we do analysis. And the ultimate decision of the utility or relevance of the information extracted at the end of the analysis process is the reference data is still taken from visually interpreted data. So it becomes very, very important to be familiar with the process of visual image interpretation. So thank you very much. With this, we come to the end of the